right, we're going to spend a little bit of time looking at some systems of linear equations in context. So how we can apply the idea of a system to some everyday situations. So a system of linear equations, like we see here, can be used to solve contextual problems by figuring out which values will satisfy the conditions set in the problem. Most scenarios will not use x and y. So let's try to get creative with our variables, right? Choose variables that are actually representing the situation. Yes, x and y are our default go-tos, right? But let's give a little bit more context to the actual equations we're creating. So first example here, a school raised $140, and we're just going to go through and highlight some of this key information as we go. By collecting 2,000 cans and glass bottles for recycling drive. They received 5 cents for cans and 10 cents for bottles. And so we have some information here, and we can categorize that into two different things, right? Remember, a system, we have to have two equations, right? Two equations, but those need to be talking about the same thing, right? We always said a system of equations is two equations in the same variables. Here, what it's really looking like is our variables are going to represent cans and bottles, because those are the two different things we're working with. And our two equations are going to talk about the two different things we're doing with those cans and bottles. We have one context, right, this first highlight that talks about the money. And we also have the second piece of information that talks about the number, right? How many bottles and cans did we actually get? And we need to know, right, to figure out how many cans we had and how many bottles we had to get us to a total of $140, right? We need to figure out how many cans and how many bottles made up that 2,000 total recycled items. Right, so let's look at our first equation. So we want to create a first equation that talks about the money raised, right? We know that our total comes to $140. Making sure we're super clear on our units. We have a couple of first things to address here. 5 cents, let's call that $0.05, right? So that we're consistent. Everything is here is in dollars. And 10 cents for a bottle, let's call that $0.10. Now we can go as far as to say, right, the 5 cents times the number of cans we got. So the 0.05 times, let's call this one C, right? Because if I get 1 can, it's 5 cents, 2 cans, it's 10 cents, right? That's our rate of change for the cans. So 5 cents per can and 10 cents per bottle. Again, we want to make sure our units are all the same, so we're going to put this in terms of dollars, 0.10. Let's call this one B. That has to sum to 140, right? That's how much money we got, and it was only made up of cans and bottles. There was no milk cartons. There was nothing else in addition to that. So we have our first equation, right? And we've determined that our variables here are C for the number of cans, right? C is the number of cans, not the cost of the cans. That was 5 cents. And B is our bottles, right? How many, number of bottles. And so our next equation, again, has to talk about the same thing. B and C have to represent the same thing. And we know here, this one looks a little bit more straightforward, right? The number of cans plus the number of bottles, so just C plus B, right? No coefficients here. We weren't altering it to change it to a different value, right? We were changing numbers to dollars in that first one. We're just talking about the number of cans here and the number of bottles, which totals 2,000. So solve the system algebraically and graphically verify your solution, right? Using one of two means, a couple of means, a graphing calculator, Desmos. What does the solution mean in context? So let's solve it algebraically first. And I have my two equations. I'm going to go ahead and do substitution because it actually looks really easy for me to isolate B or C in that second equation. And it doesn't look so straightforward to get those coefficients the same because we have those small decimals. So I'm going to take that second equation and I'm going to write it as C equals 2,000 minus B. Right? I'm going to bring the B to the other side. Now I have a new expression for C. I can call something C. I can also call it 2,000 minus B. So into that first equation, I have 5 cents worth of cans. So 0.05 times, and now I'm going to replace that, right? I'm going to substitute in 2,000 minus B plus 10 cents, right, as a dollar value, 10 cents times the number of bottles, and that has to equal 140, right? We're trying to figure out, in this case, B first of all. So we're going to give myself a little more room here. Okay, now that we have a little more room, let's keep going. So I'm going to distribute that in 0.05 times 2,000. We get 100 minus 0.05b plus 0.10b equals 140. And we can combine those like terms. Right now I have a negative 0.05b and a positive 0.10b. That's going to total to a positive 0.05b equals 140. Bring that 100 to the other side. I can subtract 100 from both sides. Just left with 40. Divide both sides by 0.05, right? And this is why it's super important that our units are the same, because if one was in cents and one was in dollars, this answer would now not make any sense. And so B equals 800. So we got 800 bottles, right? We need to know how many cans. Now, because this is in context, right, we already know that we got a total of 2,000 cans. So that tells us we have to have 1,200 bottles. That's really us, right, thinking through the algebra in our head. We're taking that equation that we have, right, that second equation, C plus B equals 2,000, and we're saying, well, if 800 of that 2,000, if C plus 800 is 2,000, and I bring that 800 to the other side, right, I lose 800 of my total to put towards the bottles, I have to have 1,200 cans. Right? We do algebra like this in our heads all the time. But this is that real application of it. This is what we're doing. Right? So those 2,000 bottles, here's what we get. And I have 800 of those were bottles, 1,200 of them were cans. Let's take a minute and look at a couple of graphing softwares. So here on Desmos, I'm going to enter the equation or my two equations. I'm going to use x's and y's just because they're here. X plus y equals 2,000. And we also had 0.05x plus 0.10y equals 140. We're going to have to zoom out, right, because we know that our answers, where they meet, is at around 200 and 800. Or sorry, 1,200 and 800. Right? Assuming that x, because that was what we put first, was our C value. So we had 1,200 cans. Our B, which we put second, which happened to be y, was our 800 value, right? Our bottles value. And this is where they intersect. Right? This is where they overlap. This is the only way, really, what this question is asking is that this is the only way that if you get $140 from the Bottle Depot, right, and you've turned in 2,000 items, it had to be 800 bottles and 1,200 cans. No other combination that totaled to 2,000 would give you exactly $140, right? You might make $140.10, maybe $138.25, right? Different amounts will only work out to, right, because it's a system. There's two set restrictions. We have two equations. So that can help us narrow it down to a specific single solution. What do the x and y intercepts represent? So let's go back and look at our graph. All right, well, the x-intercept of this blue line here, right, what this is representing, again, remembering that x was talking about our C values, our cans, y was talking about our B value, our bottles. this is saying, right, that if I have 0 X's, if I had 0 cans, right, and I had 1,400 Ys, I had 1,400 bottles, I would still get $140. Right, this is telling me the amount of bottles that I could get for $1,400 on the, or sorry, $140 on the other side of things. Right, if I'm looking at my red line, remember this was talking about the number, it wasn't telling us dollar values at all. So this one's saying that if I have 0 cans and 2,000 bottles, I have 2,000 items to redeem. Right? Whereas when we look at the y-intercept, remember y was representing bottles. If I have 2,000 cans and no bottles, right, if my y value, in this case my b value is 0, right, I have 2,000 items. Right? Pretty straightforward, but that also tells us everywhere in between are ways that total up to 2,000. Right here, I could have 400 cans and 1,600 bottles, but because it's not intersecting that blue line, it's not going to total to $140 because this blue line is representing the money side of things. And its y-intercept is saying, right, over here we said if I give you 0 cans, right, and 1,400 bottles, you can get $140. This is the opposite side of things. If I give you 2,800 cans and 0 bottles, still going to get $140. Right? Everything along this line are different combinations where I can get $140. But this is the only one where I've specifically donated 2,000 items on the nose. So let's put that into words. Right? Our x and y intercepts represent, right? So cost or amount when we have 0 bottles or cans. And specifically in that case, our y-intercepts, right? Because remember, y was our bottles, right? That tells us when we have no bottles, how many cans do we have, right? Or what could the price be for those cans? And for our x-intercept, that was what happened when we had no cans, right? How many bottles were we donating? How much money could we make when we had no cans? What would be an appropriate domain range for this situation? Remembering that domain, right, this was talking about our cans, that was our x value in this case, and bottles, right, that b value, is going to be talking about our range. So looking at this system, right, thinking about cans for our domain, well, the least number we can have is 0, right? The least number of cans I could turn in would be 0 cans. I can't turn in a negative number, right? But we looked at those x and y intercepts, right? We said what would happen if I turned in 0. And then when we look back at our system, hypothetically, the highest x value we have, right, the highest number of cans I could turn in, looks like it would be 2,800. So that's going to be our upper limit on our domain, right? The restriction on cans. Anything above that, it would be larger than the amount of money we're taking in, as well as the number of, it's already higher than the number of items we've turned in, right? But that's that upper bound. Our range for our bottles, again, same idea here. I can only go, right, down to 0. I can't get any bottles when I go to the bottle depot. I can only turn them in. And then when we look here, right, we're looking at our range, our y values. And it looks like the highest value we get, right, is 2,000. Again, the most cans I could possibly turn in. Most cans are bottles. So for 2,000 is our upper end for bottles, right? Putting restrictions on these, making sure that we're super clear, right? Our domain is referring to cans. We don't want to switch back to x's and y's now, because in the whole rest of the equation, right, the whole rest of the question, we didn't talk about x's and y's. Right? We want to continue to talk about the same variables we're using. And in this case, technically, C is not an element of the real numbers. Technically, right, C has to be a whole number. Right? You can't turn in 1.3 cans. Right? And same with bottles. Bottles is also technically a whole number, if we want to use the fancy W to represent the set of whole numbers. Right? We could also call them natural numbers, but we need to include that 0. So let's look at the last question. We can also use our knowledge of systems to relate a linear system to a problem. So, a bicycle has 2 wheels and a tricycle has 3 wheels. Create a situation about wheels that can be modeled by the linear system below. So we've got our system already. Let's talk about what it might be referring to. So in this case, right, we're seeing a couple of equations both talking about B and T, assuming that B represents bicycles, right, and T represents tricycles. We're saying that 2 B's and 3 T's equals 100, right? Well, we can assume here that those 2's and 3's are representing the number of wheels. So in this case, this equation, right, because we see those coefficients talking about things we're familiar with, right, 2's and 3's for bicycles and tricycles, this equation has to be talking about the number of wheels, right? And so maybe B and T just represent how many tricycles we have. And so in this case, number of, what do we call bicycles and tricycles together? Let's call them cycles. There. Right, so we're saying that I've gathered, right, all of the kids in the town have gathered together at this super cool child bicycle tricycle rally, something cool like that. They're in a school parking lot, it's great, there's lemonade stands, and so all the kids have gathered, and someone goes around and they say that the total number of cycles, right, coming from this second equation here, the total number of cycles is 40, right? So 40 kids show up, right, to this super fun event. And then over here, someone says, well, I went around and counted, and out of all of those cycles, right, there were 100 wheels total. Right, and so what this is, right, it's telling us there's 40 vehicles, right? There's 100 wheels total. The solution to this, right, finding out the variables B and T, would be telling us how many of those 40 vehicles are bikes, how many of those 40 vehicles are trikes, so that we have exactly 100 wheels. Right, explain the meaning of each variable, so we went through that. Let's try and solve this ourselves. Right, let's see how many bikes are there, how many trikes are there. We'll try elimination this time. So 2b plus 3t equals 100. I'm going to quickly double this second equation so that I get that coefficient of 2 in front of b. 2b plus 2t equals 80. And then I'm going to subtract. So my b's are gone. 3t minus a positive 2t, I'm left with 1t. 100 minus 80. And here it actually did the work for me. I find out that there are 20 tricycles. We do a quick substitution into either of these equations. Let's just put it in that second one for ease. So the bicycles plus 20 tricycles equals 40. And it actually looks like there's an even split here. Right. At this event, we have 20 tricycles and 20 bicycles are there. And it totals up to 100 wheels. If all of the tricycles have 3 wheels, right, that's 60 wheels coming from the trikes. All the bicycles have 2, that's 40 wheels coming from the bikes. That gives us that 100. Right, so let's quickly just brainstorm one more equation that we could create. So you're walking down the halls of a local Calgary high school, and you are looking at the number of scrunchies and the number of water bottles belonging to a group of Visco girls. And so you find out that there's 200 of them, right? Of all the scrunchies and all the water bottles, there's 200 total. And they're probably in different ratios. depending on the person. Start to think about the cost, right? And the average cost per scrunchie is about $6. And the average cost of the water bottles, right? They're pretty nice water bottles, is probably about $35 for those nicer Swell or Hydro flasks. And so the total cost of all of that merchandise is about $14.90, right? Almost $1,500. If we solve this one, and I've decided just to solve it graphically, right, looking for that intersection point, where are these two equations the same? And it looks like we have an S value of 190 and a Y value of 10. So S equals 190, not Y, sorry, our W value is 10. Right, so about 190 scrunchies for every 10 water bottles, right? You're going to wear more scrunchies. You're not going to own multiple water bottles or have them at school, right? And if we're assuming that every single person has a water bottle, you're looking at 19 scrunchies running up the arms of each of these Visco girls. And so that wraps up our problems in context. If you have any questions, be sure to send me an email, drop by your virtual classes. Completing the assignment that